So the formula below is what was developed by Karl Pearson to measure the strength of the linear relationship between two quantitative variables. Now, if we had to make these computations by hand, which remember we don't, statistics using technology, so we're going to use technology to get these numbers, we would first need to convert all of the x-coordinates into their corresponding z-scores, which we learned how to do that in Chapter 1 by subtracting the mean and dividing by that result by the standard deviation. And then we'd have to do the same for all of the y-coordinates. We would subtract the mean of the y-coordinates and divide by the standard deviation of the y-coordinates to each of those. But again, we're going to be using technology to compute this, but I do want us to look at the formula here just that we can see that it does use z-scores. So each ordered pair, we get its z-score for the x-coordinate, and we would multiply by the z-score of the corresponding y-coordinate. And again, in stats, that big sigma means to add them up, to sum them up. So we'd find all these products, we would add all those up, and then we would divide by little n minus 1. Okay, so again, this formula is using unitless z-scores. So at the end of the day, the final result for R has no units. But again, keeping in mind, we are not going to be using this formula to compute them. We're going to use our technology to get those values. So this linear correlation coefficient is a number that describes, that measures, the strength of the linear relation between two variables. Now it's important, this one only measures the strength of a linear relationship. So if we're looking at the scatter plot and there's definitely a relationship, but it's a curved relationship, okay, R might not come out to be a very strong value because the relationship between those two variables is not linear. So this is also called the Pearson correlation coefficient after Karl Pearson, who developed it. And the symbol for the sample linear correlation coefficient is R. Okay, so here is a new symbol for our symbol list. And that one's for the sample. The population correlation coefficient is the Greek letter rho. So this kind of looks like a fancy lowercase p. So this formula, if we were to have to compute values of R, that value of, using the formula versus technology, R is always a number between negative and 1 inclusive. Okay? R being equal to negative 1 means that we have a perfect negative linear correlation between the two variables. Now with real world data, that's never going to happen. When R is equal to 1, then we have a perfect positive linear correlation, which again, for real world data, we're not going to see that happen. But the closer R gets to 1 or negative 1, the stronger the linear correlation is between those variables. And the closer R is to 0, the weaker the linear correlation between those two variables is. Now we need to be careful when R is 0 or close to 0, because that does not mean that there's no correlation. It just means that there's no linear correlation. So there might be a very strong curved pattern like in the last graph on the previous page. Okay, so we need to keep in mind in this course we're just strictly focusing on linear relationships between two variables. Now there are many conditions to check for linear correlation as we start doing inferences in one of the later sections. In this level of a course, we're just going to look at checking the following assumptions. These are the same assumptions we had in the last section for regression. So again, we're just going to make sure that the set of XY ordered pairs is a random sample from the population. Of all such possible xy pairs. And the one graph we're still looking at is the scatter plot, and that scatter plot of x versus y, we want that to have a roughly, it's not going to be perfect, linear pattern with no outliers. Now we're going to get a hypothesis test in section 10.3 to tell us if what we see is linear enough or not. Now the value of the sample linear correlation coefficient is on the same output screen that was used in the last section to get the equation of the best fitting line. And the sample linear correlation coefficient is computed from unitless z-scores, so it is a unitless number. So when we get a value of r, we're going to get some number, but then there's no units. Okay. And this number that goes in the blank here is going to be a number between -1 and 1. In theory, inclusive of those numbers, but in reality, with data, we're not going to get something as perfect as -1 or 1.